Our first talk, we are hosting Marco Campion from University of Sorbonne that is going to talk to us about abstract interpretations.
Thank you. Okay. Okay, so error propagation in numerical analysis refers to how perturbations in the input data affect the output of a computation, and also how these perturbations are affect the subsequent computation of other computation. And this reasoning can also be applied to abstract interpretation in general. So, for instance, consider an abstract interpreter. We can consider how perturbations to the input data of the abstract interpreter, how these perturbations are propagated by the abstract interpreter in the output, and how this perturbation is propagated while analyzing the program inductively on the syntax. So what we want to show in this talk is actually that it is important to study error propagation in abstract interpretation, because we want to show that in order to study the imprecision generated by an abstract interpreter with respect to a concrete computation, the notion of error propagation, so the notion of this propagation of the perturbation, is essential. So why? Well, because if we have an abstract semantics which is precise with respect to a concrete computation, so we have in this case completeness with respect to a program P1, and we have also that the abstract computation is precise with respect to the program P2, then we get at the end that the composition of the two programs, the abstract interpretation of the composition, is also precise. The problem is that if we have imprecision over the first program P1 and another imprecision over another program P2, what will be the result? So how this imprecision propagates in the computation, in the sequential composition. So we want to show here that we want to show here that understanding how error is propagated by an abstract interpreter is essential in order to understand how it is imprecise an abstract interpretation with respect to a concrete computation. So here, the error propagation of the abstract interpretation of the program P2, which could be propagated, for example, linearly. So we have a kind of Lipschitz continuity, or in a cubic way. And in general, actually, we model this error propagation through the notion of omega continuity. So the notion of omega continuity applied to an abstract interpreter. So our contribution is twofold. I will show actually that I will propose an omega continuity logic that could derive could derive on the structure of the program this omega, so this modulus of continuity, and then we will use this omega continuity notion in order to derive the imprecision of an abstract interpreter inductively on the program syntax. Okay, so we'll start with the definition of the omega continuity with respect to a semantics of a program. So the ingredients are partial order sets over a domain D, and a distance of interest over the elements of this partial order. So we require that this distance satisfies the if identity and the triangle inequality. And also we require a form of compatibility with the partial ordering. So why? So the first two axioms actually represent, say that the matrix is actually a quasi-pseudo matrix in mathematics, while the last axiom actually requires a form of compatibility with the partial ordering, because it requires that the distances between the two extremes of a chain is always greater than the distance between intermediate elements. So this is essential in order to understand the imprecision over a chain of elements. So let's see an example of classic distances over partial ordering, especially over abstract interpretations. We have, as a domain, we consider the domain of intervals, so finite and infinite intervals over integers. And as a distance, we can consider, for example, the counting distance, which is the absolute value of the difference of the cardinality of two intervals. Or, for example, the volume distance. So if we have like an hyperrectangles, in the domain of hyperrectangles, we can consider, for example, the absolute value of the difference of the volume. So in abstract interpretation, for example, we want to understand what is the difference between the volume of an invariant, of an abstract invariant with respect to the abstraction of the concrete invariant. So what is the general definition of omega continuity to a general function f over a partial order? So we have this omega, which is an order-preserving function, which is 0 at input 0. And this omega is called the modulus of continuity. Then we have a function over the partial order d, and we say that this function is omega continuous whenever the distances of the output, so of the result of the function, is always bounded by the omega applied to the distances of the inputs. In particular, we can instantiate this definition with the program semantics. So we get an omega continuity definition over the semantics of a program that I'm going to define in the next slides. But in particular, what I want to define is to try to derive this omega inductively from the syntax of the program. So I will consider as a toy language for the rest of the talk, the language of regular commands. So we have the basic commands, so the skip, assignment, and the boolean guards. And then we have the program actually. So our regular range is composed by the composition, the join, and the clean iteration of the program. So as a syntactic sugar, we can build an imperative language with the if then else or while do. Then we consider a complete lattice and an order preserving semantics over the basic commands. So here the standard definition, we have the composition of two programs. We have again the join, so the O plus is the join. Then the clean star is simply the infinite join. Yes, it's the infinite join of all the possible iteration of a program P. So how can we derive this omega through the program, to the program struction, in order to derive a definition of omega continuity for the program semantics? So we'll define now the logic that we propose. So the logic is composed by three base rules. We can say three simple rules. So the base case, which says that if we have an omega continuity proofs of the base case of the base commands, then we can derive, of course, the omega continuity of the raw semantics of the base commands. We can weaken the modulus of continuity omega with a bigger omega, and we can compose two programs, and we obtain as a new modulus of continuity the composition of the two functions. So the joins here is more tricky because we need to consider the distance between the join of two computations. So in this case, the join is obtained by applying a join bound operation over the two modulus of continuity of the program P1 and P2. And this we show that this highly depends on the structure of the domain and the distance that we want to use. So in this case, consider this scenario. So we have four elements with the distances between x and y, then z and v. So what is the distance between the join of the respective elements? So we need a definition of a join bound, which poses a limit on this distance, which depends on the distance on the x and y and z and v. So this highly depends on the domain and as the distance that we choose. For example, if we consider the domain of intervals, as we shown before, and we consider the distance that counts how many more elements has one interval with respect to the other, so we do the absolute value of the difference, then we can choose as a sum join bound that respects the definition is a sum. So we consider the sum, and the same happens, for example, with the volume distance. Finally, we have the rule iterate for the clean iteration that is simply apply an infinite number of join to the omega continuity in order to derive the modulus of continuity. So let's see a very simple example. We consider the absolute value, the program that calculates the absolute value of an input. So we want to calculate the modulus of continuity of this program with respect to the abstract semantics over the intervals by considering as our distance function will be the distance which calculates the absolute value of the difference between the cardinality of two intervals. So we use the logic that we propose in order to propagate the omega through the program structure. We start with the base case by considering the guards and the assignments. We get that here the distance is not modified. So we have the identity as an omega continuity. Then we can combine the two with the sequential rule, which still it is an identity. We can do the same here with the right part of the join of the program, and then we can apply the join. So with the join, we obtain, since we have chosen the distance, the counting distance here, we know that we can do the sum of the two omega, and so as the final omega modulus of continuity, we can do the sum of the previous one. So we get 2t as a final omegas as a final definition, which is so this one. Okay, so let's see why it is important to understand how a program semantics, how an abstract interpretation propagates this perturbation. So I want now to use this information in another logic that actually propagates the imprecision of the abstract interpreter with respect to a concrete computation in this case. So now we are in the abstract interpretation framework, and I will call this logic the error propagation logic. So let's put a bit of context. We have the abstract interpretation framework. So we have a concrete computation over a concrete domain, which could be like this concrete computation could be uncomputable. Also, the concrete elements could be something non-decidable. And we have an abstract computation over some approximation of the concrete domain. And we assume that this abstract computation is sound. And we assume also a Galois connection between the concrete and the abstract domain. So what is the most desirable property in abstract interpretation is completeness. So whenever we have the equality between the abstract interpretation and the concrete and the abstraction of the concrete computation, we have completeness in this case. And I will indicate completeness with this symbol, with this big C. So the blue will be the concrete computation, while the green, I will also use the green for the abstract computation. Why completeness is a problem in general in abstract interpretation? Because when we consider an abstract computation, which is an always terminating computation, for example, in static program analysis, and as an abstract domain, when we consider a set of decidable properties, completeness is a very hard property to achieve, or even impossible. So instead of studying completeness here, we want to study the imprecision. So we want to study the difference between the invariant calculated so the result calculated by the abstract interpreter with respect to the abstraction of the concrete interpreter, and this imprecision we quantify by a distance. So by the distance that they have defined before. In particular, what I'm interested is understand what is the imprecision for each input that we are going to analyze. So I want to prove this inequality. So for every input, I want to know an upper bound of the imprecision with respect to that input. So I want to calculate this function, this bounding function, over the inputs of the concrete domain. So I would say that whenever we have this bounding function E, so when this inequality holds, I will say that the abstract interpreter is E partial complete, as an E partial complete approximation with respect to the concrete computation. And I will use this symbol, so this big C with the E, in order to define the partial completeness with respect to the concrete and the abstract computation. So let's see a very simple example. We consider again the interval domain. We consider the counting distance. As a concrete semantics, we consider a standard reachability semantics over the power set of the integer. And then we consider a standard interval semantics, which the two domains of the power set of integer and the intervals are related by a Gola connection. So I want to analyze the imprecision generated by the interval analysis with respect to the concrete computation for the program, for the absolute value program. So I want to understand what is this difference between the two invariants. Can I derive this bounding function for every possible input? So in general, we can note that the worst case is when, as an input, we have two numbers with the opposite sign. So in this case, the distance is for example, -7, 7. As input, we get a distance 7 because the abstract domain, the abstract computation produces 7 more elements with respect to the concrete one. So we have imprecision. And in general, we can model this imprecision for all inputs by defining a bounding function, which simply say a sound bounding function, which simply states that the result is the maximum of a set whenever this maximum is positive. And so we can say that the abstract interpretation over the interval of the absolute value is an partial completeness approximation, complete approximation of the concrete computation. So the problem is now try to derive this bounding function inductively from the program structure. So how can we obtain this bounding function over the program without actually knowing without actually executing the program or analyze? In fact, we are analyzing the program analyzer in this case. So we propose an error propagation logic, which requires a program. We have a program P. We have an input over the concrete domain. We have a concrete semantics, so over a concrete domain, and then abstract semantics, a sound abstract semantics over an abstract domain. We have a distance of interest, so we decide the imprecision that we want to measure with the distance. What we want to derive is this predicate, so E bound. And this predicate holds whenever this function provides an upper bound of the imprecision over all the elements that are in this chain, from G to the closure, so to the abstraction of G. In particular, as a consequence, if we can derive that the imprecision over this input G is 0, then we can also say that the abstract interpreter is precise, can precise analyze all the elements over this chain. So let's start by, I will show now all the rules. In particular, we have the base case. So we assume that we have a derivation. We assume that we have a predicate for the base commands. Then we can apply the switch, so we can change the input of our abstract interpretation, and we can consider here as a derivation the minimum of the imprecision that we derived over another input. And then we have the sequential composition that is the key point here, because in order to derive the distance between the concrete and the abstract computation, we need to understand this chain of computation. So the results of the imprecision can be obtained by a sum between the imprecision generated by the abstract interpretation of program P2, where here we combine the result of the two computation by using a partial correctness tripole and an incorrectness tripole. So here we use the imprecision generated by the abstract interpreter P2, and we sum with the propagation of the error that is produced by the abstract interpretation over the program P1, propagated by the omega continuity of the abstract interpreter P2, that is part of the logic. So this is the final bounding function derived in the logic for the sequential composition. For the joint bound, in this case, we consider here the same joint bound that I've defined for the omega continuity. Here it is applied here to join actually the imprecision over the two computation. While for each iteration here is a little different, because in order to calculate the distance between the result of the concrete and the abstract computation, here I will consider another approximation of the concrete computation with post. and an over-approximation of the abstract interpretation. And so I can take as a sound distance here the distance over the whole chain, over the whole chain of elements. So I will show a final example. Let's consider the sequential composition over the absolute value program and the clean iteration of this program F. So I want to calculate here the difference between the distance. So that I want to calculate here the distance between the abstract interpretation over this program, over the boxes, and the concrete computation, starting from an input G, which is only 2 points, which when they are abstracted are a rectangle. And I want to use the area. So I want to calculate the difference in the area of the invariance. So here I will start by inferring. So I will start by deriving the omega continuity of the program F. So we have the base case for the So we have the base case for the Boolean guards and for the assignments. Here we combine with the sequential composition. We get a quarter of t, and then finally with the iterate we get 4/3 t for the clean iteration of the F. Then we apply the iterate from the error propagation logic in order to obtain the imprecision of F star, of the clean iteration of F. And finally, we use all the information that we collected in order to apply the sequential composition between the two programs. So at the end, we obtain an area of value of 52. So what does it mean, this number? It means that the difference between the area of the two invariants is limited, the upper bound is 52. This bound could be also imprecise because we used as another approximation, we use a single computation of the concrete, a single iteration of the program F in this case. So we can improve this result by applying by using a more precise under approximation in this case. So by concluding, we propose an error propagation logic, which is the combination of correctness, incorrectness, and omega continuity logic in order to understand the imprecision of an abstract interpretation. And so we provide a way to formal model the imprecision of abstract interpretations. Thank you.
Yeah, so thanks you for the talk. I was just wondering, when you show like the join bound, the operator that combines the joins, like you showed a diagram that looks like kind of triangles. So I wanted to ask, can you give us an intuition why you can't like derive, like you need an operator that is specific for the domain, and it's not like just generic using, I don't know, triangle inequalities? Okay.
Well, in fact, here the join bound here is very dependent on the domain and on the distance. So in fact, you have to prove that if you want to use a join bound soundly in the program logic, you have to prove that actually the join bound respects the definition that I provided in this case in the paper. So it respects that the distance between the two joins is always it provides an over approximation of the distance of the two joins over the elements.
Okay, I see. Thank you.
I was wondering what abstract domains you applied this to, and what the join bounds looked like for them. Which ones lose a lot of information and which less?
So in our examples, we used only numerical domains. And so we applied them to like the standard ones, so like intervals, hyperrectangles, and octagons. And so the problematic point is when, of course, you use the widening. Because as soon as you apply the widening, you get like very easily like infinite imprecision. So in order to understand how the imprecision propagates, we consider like a kind of threshold using a threshold widening to see like finite imprecision, how it evolves in the computation. So we consider in this case only the numerical abstract domains.
We have time for one more question.
Thank you for the great talk. So is this also applicable to abstract domains that are not numerical?
Yes, actually we formalize everything by not requiring numerical. So what we only require is like an order preserving concrete computation and a sound abstract computation, not necessarily order preserving. So we don't require any numerical domains. It could be generalized.
Okay, thank you.
All right, let's thank the speaker again.